I'm going to get started in the interest of time. Welcome everyone to our Lockheed Martin seminar series. So thanks again to our sponsors for putting together this wonderful series for us. Today's speaker is Dr. Julie Shah. She is an associate professor of aeronautics and astronautics at MIT and the director of the Interactive Robotics Group, which aims to imagine the future of work by designing collaborative robot teammates that sort of enhance human capabilities. She is expanding the use of human cognitive models for artificial intelligence and has translated her work to a number of manufacturing assembly lines, healthcare applications, transportation, and defense. Before joining the faculty, she worked at Boeing Research and Technology on robotics applications for aerospace manufacturing. Professor Shah has been recognized by NSF with a career award and by MIT's Technology Review on its 35 Innovators Under 35 list. Her work on industrial human-robot collaboration was also in Technology Review's 2013 list of 10 breakthrough technologies. She earned her degrees in aeronautics and astronautics in autonomous systems from MIT. She also, this week, published a book, which I find really cool, on what to expect when you're expecting robots. Anyway, so just a little plug for that. And with that, I will turn it over to Professor Shah.
Thank you so much. Thank you so much for having me. It would obviously be much more fun to be down there in person and meet you all in person, but I'm happy to have the opportunity to do this and interact with you this way and then maybe meet in person another time. I will go ahead and share my screen here today and pull up my slides. Let's see. And can you all see that okay? Wonderful. Yeah, I'm Julie Shah. I'm faculty in Aero Astro here at MIT and in the Computer Science and Artificial Intelligence Laboratory. And I'm an AI researcher and a roboticist. And my lab focuses on developing machines and robots that are more capable teammates to collaborate with people. Starting from the broader picture, the vision behind my lab's work is to be intentional about developing computing that augments rather than replaces human capability. I'll start by saying, I've worked for many years in industrial applications in developing and deploying collaborative robots that work alongside people to help build planes and build cars. And I'm showing pictures here of two applications of real world, what I see as very effective human robot teaming. So one is one of Amazon's warehouses where these Amazon robotic systems, they're really robotic kind of shelves, and they're moving the product to the human pickers at the edge of the warehouse. Then someone does the hard dexterous task of picking the materials off the shelf, boxing it, and shipping it to you for delivery. But it is a really brilliant, really excellent decomposition of human robot work in that it parses out the work sort of tasks spatially. I think the key thing to note here, though, is that while this is a form of collaboration, it is a form of teaming. The humans and the robots are working in physically separate space. The picture on the right is a robot from one of BMW's automotive factories on final assembly. And this is, a collaborative robot. It's inherently safe so that you don't have to put cages around it. If it hits a person, it won't permanently harm them. But I think the other key thing to note here is that this is not a system that's really working interdependently with a person. It's coexisting. It's doing work next to a person, but in a more, operationally flexible way. These types of systems, exist at large scale around the world. There are somewhere around like 1.7 or 1.8 industrial robots in operation around the world today. And that's the same as the human population of Boston, Pittsburgh, and San Francisco. So it's a lot of robots in our factories. Maybe if you were to take a guess, how many robots would you guess are in sort of US homes today? Not around the world, but just in US homes. If there's 1.8 million robots in a factory today. Okay, call out a number. I don't know, I won't be able to see anything in the chat, unfortunately. Well, let me see. If I click chat, let's take a look. 0.9 million. Okay, any other guesses? Well, let's not count devices such as Alexa's, Google Now's, etc. So things that you would recognize physically as a robot. I'll take one more guess. 25,000. Okay, so this is gonna blow your mind. It's actually 30 million. 30 million robots in US homes today. That's a lot of robots. And again, as I mentioned, like that's not counting like the Alexas, et cetera, like smart home technology. It's not counting, the new, there's not the new growing number of sidewalk delivery robots. It's not counting security guard robots or if anybody's come across these strange supermarket robots with the googly eyes. They sort of roam up and down the aisles of supermarkets and hundreds of supermarkets across the country looking for spills. I personally encountered them in the suburbs outside Boston. And so we actually do have a lot of robots in our everyday lives today. And I think it's an interesting question to dig into. Why don't we feel like we have that many robots? And it's in part because these robots are performing very narrowly defined tasks in controlled environments and essentially under constant human oversight. So they're like limited tools for us. They don't really sort of imprint our minds in the way we would hope, and they're not delivering the value that we would hope these robots would be able to deliver to us. And so in some sense, much like many of the systems we see in the industrial world, they're operating in a way that's really not interdependent with us. And that cuts off a huge portion of the value that they can potentially deliver to us. So here's a question, like what are the consequences of continuing down this path where we develop robots that really don't model or fundamentally understand us or are not capable of sort of integrating into our more human world? So I'm pulling this slide here. This title of this slide is taken from a news headline about 2 years ago. So in December, about 2 years ago, there were actually so many startups testing sidewalk delivery robots on the streets of San Francisco that the elderly and people with disabilities came together to the city and basically said they felt unsafe on these sidewalks. And the city banned them. They relegated them to an industrial sector away from the most populated areas of the city. And then they put limits on the number of these systems that could be operational on any block at a time. And so this is the canary in the coal mine, the way I think about it. To some extent, the folks that complain about these systems sort of getting in their way on their walk to work or needing to navigate around them are right. These systems really don't understand the sort of complex nuances of what makes our city sidewalks work. The norms, the sort of very subtle social interactions that make this easy for us. And frankly, they do potentially pose a safety hazard. So also about a year or two ago, there was an incident you may have seen in the news where a security guard robot, I think it was at a Palo Alto shopping mall, actually trampled a toddler. And this is another example of, that's trampling a toddler is equally horrendous to, a vehicle hitting a pedestrian. And it's because, how does a toddler behave with anybody with kids? Like, they're not going to behave like anybody else. They're not going to sidestep around the robot. They might not even have a conception of how the robot will behave. They'll be drawn to it. They'll be curious. And that was, one of the roots of the issues there. So, so this is concerning, and this is something that, if we want these robots to move out of our factories and into our daily world, we really need to address these integration challenges. My lab's work at MIT is primarily pushing forward the AI side of it, so making the systems more capable of modeling humans to better integrate into natural human workflow. And I'll discuss at the end, there's a flip side to this too. There's thinking about how we adapt our infrastructure and how we need to sort of change our norms to be able to accommodate these systems at scale in society. But I'll go deeper to the AI side because that's the work of my lab. So as opposed to a system that sort of just sees us as obstacles and that we have to negotiate. We're sort of driven in my work by trying to understand effective human teamwork and be able to translate insights about what makes effective human team members into computational models and algorithms that make machines into better team members for working with people. And as I mentioned, I've spent a lot of time on shop floors in automotive, for example. And it is quite a challenging task to get 3 people to work together on these tasks. It's there's a fluidity that comes with repetition, with training. Switching someone out sort of changes that. And depending on the type of work, I've also spent time studying automation for building large commercial airplanes. The work can fundamentally change day to day or shift to shift depending on the team. And so, this idea that we can sort of, take a person out of this environment and put a machine in, it's not only about making a system that's capable of doing the task. It's about making a system that's capable of interfacing and understanding humans and the workflow. And so, as you may know, I am from the Boston area. And so I do, use Tom Brady as an example of outstanding team leadership or teamwork. And so, they say he sees and he knows. So if we try to think about what makes an effective a human partner, we need to be able to know what our partner is thinking. We need to be able to anticipate what they'll do next. And then we need to be able to make fast adjustments when things don't go according to plan. And so we work in developing AI models and algorithms that are able to do that, that are able to infer human mental state, learn through experience and practice how others will behave, their intent, and then actually can take that information about the task and the other team members and then play the game. And so we do that in 3 phases. So critically important to effective teamwork is forming a strong shared understanding or shared mental model of how it is you're going to work together and what you're going to do. So we work on developing systems that sort of integrate and enhance human team planning, sort of huddling around and developing the game plan, our emergency responders, coming around a map and making their plan. But no matter how far we get in shoring up a strong shared understanding in the planning phase, we're never going to elaborate all of the details, all of the contingencies, and those plans ultimately need to change based on our real world experience. So the next step is to take that initial understanding and be able to refine our models of others and the task through experience, practice, and training. And this is a critical key to effective teamwork. There's enormous effort placed on the processes for training pilots and co-pilots in a cockpit, or military teams, or nurses and doctors in a surgical unit. And we know we need to do that. We have well-honed processes and practices for training and refining our plans for working together as people. And we also know we need to train with technology. It's unreasonable to expect someone to just know how to use a new automation system out of the box. And so similarly, these systems need to be able to learn from how we do our work and be able to refine their models through experience, practice, and co-training. And then finally, we need to take all that and we need to play the game. And that requires something different. It requires more than knowing how to do the task or what your partners will need or how they'll behave. It requires a whole different set of techniques for actively monitoring progress through a task, activity monitoring, predicting in a fine-grained way where someone will be at what time, and then being able to efficiently use that information to make changes in the sequencing, timing of what one does to contribute to the team's success. So today I'm going to highlight just a few pieces of work in the sort of refine category and in the execution category. And one of the key themes of our work is to try to understand how it is humans do this effectively and take insight from cognitive science, cognitive models, and behavioral psychology to design structured learning models or models for inference so that machines can learn with relatively little data as a human does how to collaborate with people. So I'll start back from a few years ago and just briefly highlight a piece of work that I'm still enormously proud of, but it sort of set off a whole new line of work in our lab. We had a project for a number of years with the hospital in Boston, Beth Israel, and the goal was to be able to develop intelligent decision support or robotic assistance for the resource nurse of a labor and delivery floor. And about the time of this project, I was pregnant with my first kid. And so I was enormously interested in learning how a labor and delivery floor runs and the challenges associated with it. It's kind of a neat rabbit hole to go down. So it turns out that these labor and delivery floors, they have these resource nurses, which are essentially the air traffic controllers of that unit. So this resource nurse is sort of the nurse leader, the charge nurse. And he or she is responsible for monitoring all these LCD screens you see here about patient status of the labor floor, as well as that handwritten whiteboard over to the right, where all the patients are written out, the assignments of nurse to patients, patient status, et cetera. So she takes in all this information and makes many different decisions about which nurses are assigned to which patients are assigned to which rooms, how things change as they progress through labor. She controls aspects of the OR schedule, many other decisions too. One of my former outstanding PhD students, Matthew Gombolay, he's now an assistant professor at Georgia Tech. This was his PhD dissertation, and he spent a year embedded with these nurses, learning how they do their job, what factors, what bits of information they use, to be able to ultimately develop a machine learning model that can learn through relatively small amounts of observation of these nurse decision making and a compact model of the rules or heuristics that underlie their decision making. It was really amazing for me to find out that these nurses are doing a job that's computationally more complex than that of an actual air traffic controller. And they do it without any decision support. So there's enormous opportunity to be helpful here. It's not, we're not aiming to replace the job of this resource nurse, but there's enormous potential to offload even some of the more simple decisions and free up their cognitive capacity for the more difficult decisions, the ones that they train for literally years or a decade or more to be able to ultimately do this job well. So this work, what we did was take insight from how human apprentices learn relatively efficiently, task assignment and scheduling strategies. And we know that humans learn very effectively via pairwise comparison. So rather than taking the sequence of nurse decisions and aiming to learn from that, the trick here was to design a pairwise ranking model to be able to infer, there's an assumption underlying this, that every decision the nurse made must have been equivalent to or better than the other set of decisions they could have made. And conversely, any decisions they did not take at some moment in time must have been better, equal to or worse than the decision they did take. And then through that, we were able to develop a model that was able to learn policies for task assignment and scheduling for this, and also in a military context with the Lincoln Lab. So I'm gonna show you an example of that system deployed on the labor floor in demonstration form, and then discuss one of the key limitations of this work that's inspired the next steps in our lab.
What is a good decision?
Right, and it kind of made me like,
I recommend placing a schedule cesarean section patient remark on. Nurse Meredith can take care of her.
So that's the full information the resource nurse takes in. We in collaboration with the hospital, developed.
what is a good decision?
I recommend placing new patients in triage bed number 5.
What is the bad decision?
A bad decision would be to place a scheduled cesarean section patient in room 14 and have Nurse Kristen take care of her.
So it's very specific.
Ginger, what's a good decision?
I recommend placing scheduled infection patients. Nurse Meredith will take care of her.
I don't know if you plan to go back and watch it. For me, it was like this for one. I always plan so much.
Ginger, what's a bad decision?
We don't know.
A bad decision is placing unnecessary infection patients who can have nurse lady take care of her.
I agree.
So that was a demonstration, which was an animal on its own. So that little robot was actually reading the live whiteboard of current status of the labor floor and making those suggestions. But we did develop a high quality simulation environment for the labor floor in collaboration with our hospital partners. We had nurses and doctors sort of play a day in their life, be given access to the full set of data they would have. The day of the labor floor would sort of evolve according to particular kind of probabilities. We were able to assess the acceptance of the robot's recommendations in that more controlled simulation environment. And we did find that nurses and doctors accepted the robot's recommendations actually 90% of the time. That's an indication that the system did learn a high quality model, which is exciting. So that's a success. So this is a system that in our view, in the nurses and doctors' views, is not able to take over, and it's not even desirable to have them take over the full role of that resource nurse. The key idea here is that the system could offload, make recommendations, and reduce the cognitive burden associated with parts of their job to make the environment safer for patients, and make nurses sort of better leverage their expertise and training. So now the key challenge is that I mentioned my outstanding PhD student embedded for an entire year on that labor and delivery floor. And the key thing is, you need to know the features that affect or that are inputs to the nurse's decision making. Everything relies on that. Ultimately, when you're deploying a robot system, there are some aspects that are observable, but there are some key factors that very clearly influence human decision making or behavior that are unobservable, that are latent. We saw that, in the healthcare situation. We've seen that in our work in industrial applications as well. Things that are latent are people's personal priorities and preferences for performing the task. The ways that fatigue or sort of changes over time may influence their behavior, or workload. There's sort of a well-defined characteristic to how workload affects someone's performance on various types of tasks. What is it? Oh, I'll scoot on here. So that inspired a line of work in which we don't just aim to learn the underlying policy of a nurse's decision making or of a person's behavior more generally, but we also aim to be able to learn or infer the implicit factors and their dynamics in terms of how they affect an agent's actions. And so, to broach this problem, I'm showing you here a graphical model developed by Vaibhav Unholkar, called the agent Markov model. And it's designed in a particular way so that we can leverage its structure for efficient inference. So you can see that this is potentially quite a thorny inference problem. Our known decision factors here, S, these are what we can observe about the state of the world. And we have A, the set of decisions that a person takes, or how they act in the world. And then what is not directly observable are these latent decision factors. We don't necessarily know how many of them there are in advance. They may be hard for a person to label or name. And they evolve based on a transition function. There's there's an initial probability, there's a policy as well. So the key thing here was to think about how we can perform efficient inference, and this model is structured in a particular way to support that. So I'll talk about how we take a sort of variational inference approach to this. For those of you that are sort of familiar in leveraging the structure of an IHMM through a variational inference process. Our approach here is inspired by that. And you can see something particularly key in the design of the structure of this model, which is how the known decision factors interact with the latent decision factors. So for example, the known decision factors, maybe where parts are on the table, sort of evolves from step to step. But we may have latent decision factors, cognitive states of the human that impact the person's actions as well. And what we assume here is that while the known decision factors may impact the latent decision factors, the sort of latent cognitive states are not going to impact the known decision factors. So just because I'm fatigued, the objects on the table are not going to jump to, say, a different location. So for many settings, this is a reasonable and appropriate assumption, and it gives us great leverage in terms of being able to approach this problem in a more efficient way. So now the challenge is that, even with this structured graphical model, we have an impossible task of trying to infer these latent variables. We have like an impossible task of trying to infer these latent variables directly from the observable data alone. In this high dimensional space, there's many possible, sort of quote unquote explanations for what we observe here. And so why do we need these latent variables to correspond to a human mental model? Well, one is it's important for communication. It's important for that system to, if that system is going to be able to project the person's behavior and generalize in a new situation, you really do want the underlying computational model to better match the sort of cognitive model that the person holds. And so the key here is that, doing this through a supervised approach is very expensive. And so the idea here is to figure out ways to better leverage human high-level input and domain expertise. So what can people easily provide? Well, it may be hard to directly label or name cognitive latent states, but we can provide maybe partial information about the dynamics involved, or partial information about the policy. Or just to give a very concrete example, it's relatively easy for a person to be able to encode change points, like when a latent state kind of changes. And that, like these sort of partial forms of input that are relatively easy for a human to provide can be used in the inference process to be able to converge on latent representation and dynamics that better correspond to the one that the human holds. So the example I'd like to use for this is thinking about how you sort of parse the behavior of a subway system. So I'm originally from New Jersey, and in New York, the subways go uptown and downtown. But in Boston, the sort of labeling of the sort of subway or the T is based on one particular station in the center, Park Street. So it's inbound or outbound from Park Street. So there's these two modes, right, that govern the behavior of this of the subway. And they're equally valuable in terms of predicting the observable behavior of the subway. But we would want a way for the latent state that we learn or that we infer to be able to correspond to my human mental model, whether I live in Boston or whether I live in New York. And by just telling you when the mode changes, as I move through Park Street or as I'm at the end of the line, uptown, downtown, that's useful information to better guide the inference process. So the way we do this is we encode this high-level domain expertise in the form of partial policies, partial dynamics, these types of change points. And if we have them, some labeled data, we use them as constraints to a variational inference process. So we call this constrained variational inference. the key thing is working through, what aspects of the problem is constrained by these various forms of constraints. So some constraints are the global updates, some constrain the local updates. But the key idea is that we're using these constraints to modify the support so that it exists within the constraint. And so in a sense, it's shaping the prior for inference. And so this works quite well. So let's give you a concrete example where we model the behavior of a person performing a sequential task sort of inspired by an assembly line task. In this case, it's a person making sandwiches, putting the sandwiches parts together, wrapping them, filling cups associated with the sandwiches with juice. In this case, the known decision factor is the position. The latent decision factor is the person's intent. And so, where they're going to reach at the various stations on the table. The action is a motion primitive, movement, through the space. And then we have our agent Markov model latent parameters, the policy, the transaction function, and the initial distribution. And so I'll show you sort of trends on the next page for this particular example, for this particular domain, but we've seen similar trends in our other benchmark domains. The subway example, the very simple one I just described to you, an agent moving along the line, as well as sort of a vehicle passing sort of simulated environment. And so, so what we see here is that when we compare the sort of constrained variational inference approach with some small amount of high-level human domain expertise or guidance to the inference process, that's hybrid in blue. When we compare that to a fully unsupervised approach, we see, in this case, looking at the weighted KL divergence, the difference in the policies between what's learned through our hybrid approach and an unsupervised approach, we are better able to match the model. We can do this assessment in a simulated domain, obviously. It's hard to do that in true human subject experiments because we can't really see into the person to compare the learned policy to theirs. In that case, we look at the action traces and look at the Hamming distance between them, and the trend is the same. So you see, we see much better convergence for the hybrid model, on par with what we get with a fully supervised model when we provide the system a fully labeled data set of the latent states or the latent factors. So, so this is exciting because this is a big step forward to us to being able to much more efficiently learn high quality human models that the robot can use in its planning. And so I just sort of presented a little bit about the human model here, the AMM. Next, we need a task model that can be specified manually by a person. But there are also reasons we might want to learn that through demonstration. And so I'll spend just a moment talking about complementary line of work in learning task models, in this case, specifications from demonstration. So, so in many of our settings, learning, doing something like inverse reinforcement learning is valuable. But ultimately, when we learn a reward function, it's often hard to parse out acceptable versus unacceptable performance of a task. So that's a key issue for us if we really have a bright line between acceptable and unacceptable behavior. So in another sense, there's specifications that specify the correct behavior, the correct performance of this task. And what we note, again, inspired from cognitive models and cognitive science, is that humans are very, very capable of looking at very few demonstrations and inferring the specification for correct execution of the task. So I'm showing you just 4 pictures here of, think of it as a vehicle driving around in a 2D world, and it's there's sort of green waypoints. So you see the green circles; those are waypoints, and then there's these red circles, that exist that are some other feature of the world. And even just looking through these 4 examples, you can extract pretty readily the specification for successful performance of this task. It's travel your way through waypoints 1, 2, 3, 4, unless one happens to be in the red zone, in which case skip it. And that's it. With these 4 examples, we can pull that out. And so our goal was to be able to enable a machine to be able to infer these types of specifications and capture this sort of notion of acceptability of the execution. And temporal logics are a very flexible language for expressing these types of task specifications. And once we have them, they're incredibly useful because we can use them to synthesize verifiable controllers. They provide a reward signal during reinforcement learning. And they're also useful for execution monitoring of the system. And so the goal here was to develop an approach. In this case, we developed a Bayesian approach for specification inference for inferring the temporal structure of a task in the form of a linear temporal logic specification. And the way we do this is to observe. LTL is enormously flexible for specifying behaviors, but the flip side of that is that it's a very difficult challenge for inference because it's a very large hypothesis space. Now, but we're not stymied by that large hypothesis space. We were able to look at those 4 examples and relatively easily infer the specification. And we have some insight into how we do that as people. So people do commonly use a subset of temporal behaviors when we're building complex systems like software systems, when we're analyzing systems, when we're designing programs. And these templates are actually there's whole papers, there's a whole community that describes them for us. And so the idea here was to take an approach where we define the prior and likelihood distributions over a smaller but relevant part of the LTL formula, drawing from the templates that are used in this, that are identified in these prior works. And so I'll pull up for you 4 templates here, or 3, I'll do 3 just to give you an idea of how this works. So these are 3 key templates in conjunction that are enormously expressive for many of the real world tasks we've looked at. So one is we want to be able to specify global satisfaction of propositions. So for example, always stay outside of some avoidance zone. We want to be able to describe eventual completions of subtasks. So eventually visit a subset of the accessible points of interest. And then finally, we want the ability to specify sequences of subtasks, maybe as linear chains, maybe as sort of forests, and depending on our selection, we approach inference differently. But we want to be able to specify things like visit a subset of the points of interest in a specific order. And so, so we developed an approach to do this, drawing from probabilistic programming to be able to sort of efficiently infer the specifications. And it relies on specifying a domain-independent likelihood function, and as well as selection of sort of different families of priors. So for example, we look at 2 priors in this case. One is a set of linear chains of subtasks, and one is a forest of subtasks. And so depending on your knowledge of the nature of the task and the nature of the precedence constraints, you could select one versus the other. And so I'm showing you the very simple synthetic domain of agents visiting for points of interest in some specific order. And so in this case, there's a few scenarios we ran. One in which some threats are randomly placed, one in which the agent needs to visit a subset of them, but in some specific order, and then the others are unordered. And what we found in this case, looking the Jacquard index, like a union intersection measure of the inferred specification to the ground truth specification, is that we're able to infer the correct specification with just about 10 demonstrations in this domain, which is really exciting. And so to give you a further sense, we look at another real world task of trying to infer the specifications for setting of a dinner table. In this case, there are sort of 8 pieces that need to be set. There's various constraints, various orders in which plates and bowls need to be set down, but maybe unordered fork and knife. There's a centerpiece that has to be avoided as you're setting down the items. And again, we collect about 71 demonstrations of people coming into the lab performing this task. And the inferred specification actually, had one additional ordering constraint than the ground truth specification, and that's that the fork be placed before the spoon. It turns out that this constraint did happen to be satisfied in all but 4 of the 71 demonstrations, and so the system extracted it. But what's really nice is that the learned representation is very human inspectable. And it's easy to make additions or modifications or drop out certain terms in that conjunction. And that provides a type of medium for the person to review and refine the learned representation. And so the other benefit of this, which is desirable for us, especially when working with a person, is that by inferring a specification, we are afforded significant flexibility in how we execute that task. So I'll show you a video here of the robot then setting the dinner table based on the inferred specification. There are multiple ways that would satisfy that specification, multiple orders. And so you see that sort of manifested here with the robot completing the task in different ways. And it provides robustness to disturbances or variation in the role of other agents performing the task. So in the next segment of the video, you'll see that as the robot is executing the task, we cover one of the objects. In this case, we'll hide some of the table objects. In this case, you can kind of see a plate on the right there covering the tag for a white plate covering the tag for one of the plates. So from the robot's perspective, it just doesn't see that plate, but there are many possible orders that it can proceed with to successfully execute the task, and it continues on to make progress on the task. At some point, when that plate appears again, it'll go ahead and continue on and finish the task. So you can see here it was blocked. That was really the next item it needed in its sequence. And now it continues on to finish. Okay, so I'll pause there for this, and then I'll just say, along these lines of work, I did notice that this seminar is sponsored by Lockheed, and actually this work was done in collaboration with Lockheed. Great project with Kevin Oden in collaboration with Patrick Craven and Kevin Landers for a project with AFRL. And so the Bayesian specification inference approach was actually inspired by this particular setting. It was to be able to develop AI that can sort of integrate or help enhance pilots' mission planning and their debrief. And so the concept would be, just as I mentioned, you plan your game plan, you refine your plan, you execute. To be able to support sort of the analysis of the execution and support the debrief, a human team, the pilots, the human pilots can get better at their job overall. And I'm going to show you this example just to give you a sense that Bayesian specification actually scales really well. So in collaboration with Lockheed, Lockheed developed a simulation environment for this large force exercise scenario. Involving many aircraft. So you could see 8 escorts, 4 that suppress enemy air defenses, and then 2 that do the strike. And these large force exercises have different phases to them. And so this is just a pictorial representation of the first phase of a mission where the aircraft are going out, a second phase called strike push, a third phase for time on target, and then an egress, and then the end of the scenario. And so, after one of these real missions, there's a process by which the the mission is reviewed, and the pilots and the commander come together to understand where the mission objectives achieved and where the tactical objectives achieved. I'm showing you here the sort of 4 mission objectives: gain and maintain air superiority, neutralize enemy IADs. Then you have your time on target, and you want to ensure that this is done with no more than 25% attrition. And it surprised me to learn that obviously they have limited time to do this debrief, but even just assessing those main mission objectives, those 4 main mission objectives, take the bulk of their time. They each review the mission, the video independently, and they come together. And there's actually relatively little time even devoted to being able to, at a more granular level, work through the tactical objectives and work through how it is, the team can work more effectively going forward. And so again, much like the nurse scenario, where the goal is to ease the cognitive burden, free up more cognitive capacity for the job that needs to be done, it's the same here. It's not to replace, but to be able to accelerate the review, the understanding of what parts of the mission were met the mission objectives or the tactical objectives, and what parts didn't. And so obviously, like, you have a beautiful model and a beautiful algorithm, but making it work in practice for something like this takes a lot of work. It takes a lot of cultivation of the data. So we have trajectories of the component level aircrafts down to the lowest level, the systems configuration. We develop a system to be able to tag the various mission phases to the labels. Then there's these sort of contracts, the coordination among the different aircraft that need to be labeled. And so we use supervised techniques to develop automatic labelers for these. And then finally, from the process data, we want to be able to infer the temporal logic specifications to understand if any particular part of the mission represented an acceptable or an unacceptable execution trace. And so this is to give you a sense of the various steps in taking the data from the simulator to ultimately get to what we need for Bayesian specification inference, which is a set of Boolean propositions about the state of the world. So levels from 1, 2, and 3 are distilled into these Boolean propositions. And obviously that requires collaboration with the subject matter experts as well. So, unlike the AMM work, now here we're back in a world where we need full knowledge of all of the features that are important to this problem. And so, these are the Boolean features that we ultimately describe for this scenario. There's global propositions that flag the level of friendly attrition, whether strikers were shot upon or shot down. Eventual propositions, so hostile attrition of various levels, weapons released, correct target attacked, etc. And then models, we aim to develop models for the 3 mission objectives listed here: gain and maintain air superiority, the time on target, and then no more than 25% friendly attrition. And so the idea was to look at the execution traces and infer the specifications that relate to these mission objectives. And I think something, again, really interesting for me to learn was that there's no codified concept, there's no codified specification for what it means to gain and maintain air superiority. So if we look at that one first, I'm showing you here what Bayesian specification inference infers from the execution traces that our subject matter experts say represented situations in which we gained and maintained air superiority. And you can see that it corresponds to at least our subject matter experts' understanding of what this should mean. You never lose more than some percentage of your aircraft. You're never shot upon or shot down. You do eventually have hostile attrition and you release your weapons, and that there are some ordering constraints, 50% hostile attrition before weapon release. And so just to give you a sense also that the output is very human interpretable, and it's very easy for a pilot or a commander to say, actually, the fork placed before the knife is not actually a real thing, like that ordering constraint doesn't matter, and just pull it out of the formula. And similarly, we sort of followed the Oh, and so I'd mentioned here, I'm showing you a video of one of the executions. So actually, this was an execution that our system flagged for the pilot. Our system flagged a particular execution that the pilot said represented gaining and maintaining air superiority, and said, actually, this execution does not meet the specifications that it inferred. And then the pilot, you could see it's like hard to like track and understand. I don't know, it is to me because I'm not an expert in this. It's more interpretable to them, obviously, but there's a lot going on here. And our subject matter expert actually just missed it. It turns out there were more than 25% friendly aircraft shot down. And so this would be a case where you wouldn't want to just brush it by and say, this is a successful execution, but you would want the team to be able to learn from that and review it. Just like any team, would want to be able to learn from kind of critical incidents. And so again, this is showing you sort of the inferred specifications for these other mission objectives. Okay, so let me move on here. Okay, so finally, we want to be able to take this all together and enable our system to kind of play the game with a person. So back to the manufacturing world or the industrial world, this physical robot like collaborating with us, supporting us. We have an ability to learn human models. We have an ability to learn and refine task models or specifications for successful completion of the task. And now we want to be able to give all of that to a robot in the form of a POMDP in this case. Enable the robot to reason over online the human latent states, the projection of the human's behavior, the successful completion of the task, and then be able to take actions, both physical actions in the world and, as is very important to teamwork, communicative actions. And so I'm going to show you a video, but pointers to works here to describe to be able to go into more detail about the cleverness that is required to make a POMDP of this size tractable, like leveraging the structure and pre-computation. But I'm showing you here a picture of one of our handover tasks. In this case, the state space is 2 × 10⁶, motion of the person through the space. And we have a planning time with the POMDP of 0.3 seconds. So the system is quite responsive online. And the goal of the robot here is to predict when and where the human will be in order to successfully complete a handover task. So to hand juice to the person or a next piece in the sandwich assembly process. And then similarly, we have a second experiment task. I'll show you the video of this one, in which the person and robot work in a shared workspace to be able to complete that sandwich making task. So the robot and person need to share the space safely and efficiently. The system needs to be able to choose its actions and communications to enable the person to mesh its actions with the robots. So in this case, the actions include both physical actions as well as communicative actions. And so in the experiments with the handover, we compared the performance of the human and robot working together with our system called Ada Coral, compared to a model which was fully supervised in terms of providing full labeled data on the human latent state, for example, versus a handcrafted model of human behavior, and saw statistically significant improvements in reward accrued, as well as statistically significant increased number of successful handovers between the person and the robot. And then on the communication side, we again saw that when the system was doing joint planning of physical actions and communication, that outperformed models in which there was no communication from the robot to the person, or handcrafted behavioral models for the robot. And so we have small experiments within subjects, but with indication of improvements in performance by sort of bringing this additional computational power and this additional modeling capability of the human. And so I'll finish out by showing you the video, the last video of sort of bidirectional communication in this human-robot collaborative task, so you can get a sense what the full system coming together looks like. So the robot's going to fill the cups with juice. The person's going to make the sandwiches. The robot's jointly making decisions about its actions and communications under partial observability.
Hey teammate, let's make some meals. I will pour juice. Please make and wrap the sandwiches. Let's start.
So the robot can talk at any point.
Please make the next sandwich at 2.
So in this case, the robot is not going to communicate to the person because it actually does have a strong belief of where the person is going to go, and can use that in its planning. So it's using its predictive model to reduce communications and that sort of bother factor.
I am pouring juice at 3. I am pouring juice at 4. I am pouring juice at 4.
So by providing that sort of status update, if it's unsure to sort of change the or unsure in terms of its ability of influencing the human behavior, and there's impact to not successfully influencing the human's behavior, juice. It will update sort of again. So you saw it sort of repeat its communication, and so. Yeah, so this is one of the recent examples, very satisfying for me because all these years my lab has been working on all these different capabilities separately, and to start seeing them coming together and being able to show the benefit to human-robot collaboration, to have them all integrated, it just is very exciting. And so with that, I've talked through some of the recent work from our lab in terms of making systems more capable of collaborating with us. As was kindly alluded to earlier, on a related topic, but I will just say broader, I do actually have a book that came out this week with basic books and what to expect when you're expecting robots. And it's looking at how we need to reconceive of technology to enable these systems to move from our factories out onto our street. And a part of this is what I discussed today, work from our lab in making the AI more capable of collaboration and understanding people. But we also address, Laura Major, my co-author, and I address in the book that it's got to be a two-way street too. We need to rethink our norms. We need to rethink our infrastructure, like down to our sort of city sidewalks, to be able to reap the benefits of these systems. No independently intelligent or capable system is going to be able to navigate our very difficult human world. And so just like we outfit factories for these systems, and we outfit crosswalks to deal with different behavior of bikes versus pedestrians, we look at the design problem in a more holistic way, understand the intersection between this technology and our society. And so I encourage you to check that out as well. And so with that, I'll stop and take any questions. Thank you so much.
Yay. If anybody has any other questions, please feel free to either raise your hand or fill in the Q&A box. So Julie, there's some from the Q&A. I don't know if you've answered those. And then some, Stephen has written something in the chat window. If you want
Okay,
to
let me see here. So you mentioned that nurses and doctors accepted 90% of the robot's decisions. Were the other 10% still optimal decisions? And why did the nurses and doctors not accept those decisions? So here is a great question. So like what is our ground truth in the hospital? We don't have any ground truth. So one key thing we would want to understand moving forward and thinking about operationalizing the system is to what extent does one nurse accept the recommendations of another nurse? And is it even 90%? And when they're not accepting it, why are they not accepting it? Are they not accepting it because it's unacceptable? Like in the sort of specification scheme, or are they not accepting it because they have a preference or some knowledge or reason to believe that another decision is more optimal? And we don't know. So it's very difficult to assess that in that real world context in the hospital. We did have the opportunity to look at a comparable data set and application with Lincoln Lab on the military side, in which we had data of military operators solving target to weapons assignment problems, like protecting like ships from incoming threats. And that's a super hard task assignment and scheduling problem that relatively few people, again, are very good at, and they struggle to figure out how to train people to do that task. And in that case, it's like a game, right? So there's a well-defined objective function to optimize. And so we don't have to rely on just acceptance, human acceptance of the recommendation. In that case, we could really look at numerically whether the policies learned were comparable to those produced by military operators and experts. And they were comparable to the average military expert, which was very encouraging.
Gil Blankenship has a question in the Q&A. In the sandwich making task, what happens if the human doesn't follow the instruction, makes sandwich number 2 and builds it at number 3, or doesn't build it all?
Yep. So so people can do whatever they want. That is a rule of thumb to like you have to make your system robust to that. And in this case, the robot will adapt. So the person can do the task ultimately in any order they want, but the collaboration will be more effective to the extent that the model that the robot holds of the person is predictive of the person's behavior. So, but people operate in different modes. You know, if you're working slowly and you're not under time pressure versus on the assembly line, suddenly you're under time pressure, you're going to change even the order, the sequencing, the movements of how you do your task. That's one of the things you'd like to learn in these latent factors, is that switching of behavior, because then it gives you a better predictive capability. But the baseline here in all our experiments and all our systems is there is a safety system running. So at the very least, the robot will not, the intention is for the robot not to contact the person, but the meshing of the interaction will likely be less efficient.
Okay, does anyone have any other questions? I have a more technical question, but I'll do that when everyone is done. Okay, we do have one more. How would you account for safety during execution? Do you have multiple planners? What was the object in the handover task?
Yeah. So we account, so in this case, all our experiments are approved by our IRB. And you know, in the laboratory, we have a safety system running on these systems that I'm not saying that's the same safety system you would use in a production environment. It's up to each individual setting to certify their system and their task. Certifying the task is equally important. But we design our tasks very carefully so there's no pinch points. We have a safety system running in the background. So as the person nears the robot will slow and stop. Then we have someone manning an e-stop. And so we take, you know, we have multiple sort of layers for safety for running these experiments. The comparable category is speed and separation monitoring in a factory. You need the system to slow and stop as a person nears. Oh, and what is the object in the, what is the handover object? It's either a cup or like a ketchup object. Melissa and Doug, like kids' toys. So there's, you know, the condiments, for example, but something that's relatively easy for a robot to hold.
Professor Celli says, can the robot tell the human you are wrong, for example, based on a very low probability of success of the human's decision?
So in this work, we don't do that. But it's an interesting question. So it turns out in our prior studies that it's a fascinating thing. Like when you explicitly command someone, people tend to drop what they're doing and attend to that command. So rather than saying you're wrong, it would maybe be more useful to be directive and give an explicit command. There's also overhead for the team. The more you explicitly command a team member, sort of well documented over in many settings that is a sign of ineffective teamwork. And so, for example, pilots and co-pilots actively train to be able to use implicit communication or implicit coordination behaviors to be able to offer status updates or information or resources before it's requested, so that someone doesn't have to explicitly ask or someone doesn't have to explicitly command. So that would, on the level of different forms of communication, that would be a last resort, but instead of just saying you're wrong, it's also just as important to be able to provide the next step, the actionable, correct next step for a person. And so it's a great question. There are certainly circumstances under which that might be the right thing to do, but we haven't looked at it in an empirical setting yet.
Next question, do the study participants in your projects indicate lower mental stress or cognitive load when working with the robot compared to working without the robot?
So we have looked in the past at the cognitive load of working with our sort of subjective perceptions of working with a robot that's adaptive versus non-adaptive. For example, you could imagine that it may just be better for a robot to behave as a robot and perform a task in a repetitive way and let the person do the work of adapting or working around that robot, as long as there's a safety system, underlying safety system in place. Like we always ask the question, like, do we need this intelligence we're aiming to develop? Like, are we sure that it's actually gonna provide us the benefit that we hope to see? So one of the very first studies out of my lab was actually a study looking at adaptive versus non-adaptive robot. And the adaptive system showed improvements on objective task measures, but actually also the subjective task measures as well. So the caveat was back then, we had to work really hard to ensure the robot's motions were repeatable to the person. So even though the robot might do tasks in a different order or move, using like an RRT planner back then was just like unacceptable, because one day, one moment the robot would reach forward and the next it would kind of move around, and then RRT star helps you, but sometimes you still get strange behavior. And so way back when, we actually pre-programmed in advance all of the robot. There was no online motion planning, so that we could remove that as a confound. And now it's much easier to incorporate other factors in motion planning to produce motions that are sort of more acceptable, more predictable, more legible for the person. But that's a great question.
I think that, one more question. In the sandwich task, can the robot recognize the skill level of the human and adapt accordingly? Very skilled human versus a naive human, like a skilled chef versus a child.
So the way that would likely work is we would probably pick up on something like that in sort of the non-parametric modeling approach of the latent state. So probably that latent state would correspond to something like novice or sort of streamlined expert. And then the robot's policy would be adjusted based on its, based on sort of online inputs of that latent state. But we have not looked at anything quite like that. We did do that demo, that communication demo, at our Aero Astro holiday party last year, where like 10 or 15 kids of faculty did the task with the robots. And so it is robust to kids doing that task with them, which was amazing to see. Very satisfying. But the model learned that we used in that demo was not a model trained from children's data, because that that would not be in compliance with our IRB.
And then what was the sample rate for updating that policy?
We update the policy at 0.3 seconds. And in this particular test, that does, it produces fluid collaboration. Depending on the task, you might need something shorter.
Okay. Any more questions from the crowd? All right. Then with that, Professor Shah, thank you very much for this engaging session. And at some point, we hope to have you come in person.
Thank you. I look forward to it. Nice to virtually see you. Thanks for having me.
Everyone, thanks for attending.